Relative extrema in the second partials test in 3 dimensions, part 1. Well, to begin with, relative extrema in 3D can come in 3 forms. We can have a relative minimum, that's at the bottom of a surface, a relative maximum, that's at the top of a surface, and also a saddle point. In all 3 of these examples, we have partial derivatives with respect to x and y equaling 0. In this case, you can see there'd be a horizontal tangent this way, and also a horizontal tangent this way. If you're looking into the board, it looks like a relative maximum. And if you're looking along the board, it looks like a relative minimum. And in these 2 cases, same thing. We have 2 horizontal tangents, each corresponding to an x and a y partial derivative. So this is how we find the critical points. And then once we find them, we can distinguish between this, this, and this using what's called the second partials test. And we'll go through a couple examples of how to use this. It's really straightforward. First of all, we're going to look at f of xy equals x squared plus y squared minus 6y. That's an elliptic paraboloid. It's just shifted along the y-axis. We would expect a relative minimum. So first of all, we're going to find the x partial, which in this case is 2x. We're going to set it equal to 0. And we're going to find the y partial, which is 2y minus 6, set it equal to 0. Very easy system to solve. We get x equals 0. These 2 equations are independent. Y equals 3. And so the point we have is 0, 3. You can plug 0, 3 in. 0 zeros that out. 9 minus 18, you get negative 9. That's the one critical point. That's all there is. And now we want to apply the second partials test. Let me clear a little space in here. And you see it's pretty easy. First of all, we want to find this quantity, d, which is the second x partial times the second y partial minus the mixed partial squared at whatever critical point we happen to be investigating. So first of all, d equals the second x partial. There's the first x partial, the second one is 2. And then the second y partial, that is 2, minus the mixed partial, which you can do a y partial of this and get 0, or an x partial of that, you get 0. 0 squared equals 4. If this were a higher degree polynomial function, this would be a function of x and y, but here we get a constant 4. So if we look, less than 0 saddle point, greater than 0, it's either a min or a max. So 4 is greater than 0. At this point, we know it's a relative min or max. So now we need to look at the second x partial, evaluated at that point. So the second x partial is 2, fxx. At this point, 0, 3 is equal to 2. It's a constant 2, which is greater than 0. And greater than 0 says we have a relative minimum. This implies that 0, 3, negative 9 is a relative minimum. And that's no surprise. I can show you what this surface looks like. We can write this as x squared plus y squared minus 6y plus 9. If you complete the square of minus 9, 6 over 2 squared is 9. And we get x squared plus y minus 3 squared minus 9. And you could draw, there's the y-axis. You could move over 1, 2, 3 on the y-axis. Without that, it's actually just a parabola here, but this is moved down. So it's down here somewhere, and it's an elliptic paraboloid. And that's the vertex of this paraboloid, the bottom, and that happens to be 0, 3, -9. And sure enough, it's a relative minimum, as this analysis suggests. Here's a couple more examples. Number 2. We'll look at a higher order, a higher degree function. X cubed plus y cubed. Fx is 3x squared equals 0. Fy is 3y squared equals 0. X equals 0. Y equals 0. So we have 0, 0, 0. You plug 0 in, you get 0. That's our one critical point. Now D, the second x partial is 6x. Second y partial is 6y. The mixed partial is 0 either way. So you get 36xy. Now in particular, D of 0, 0 is 36 times 0 times 0, which is 0. So which case do we have? Less than 0 or greater than 0? Well, guess what? It's none of the above. D x0, y0 equals 0. Test fails. Okay. Pretty much end of problem. Okay, you can graph this and see with some sort of graphing utility, but there's no simple analysis we can do to follow up to determine whether this is a relative minimum, maximum, or saddle point. It's just a plain failure. Okay, number 3. F of xy is x squared minus y squared x plus y squared. These nonlinear systems can get quite interesting. We have fx is equal to 2x minus y squared. We can set that equal to 0. Fy is equal to negative y squared x plus 2y, set it equal, oh, sorry about that, I made a mistake on that term. Negative 2yx plus 2y equals 0. A couple different ways we can proceed. You can factor and then substitute, doesn't really matter. How about if we factor this? We get 2y and negative x plus 1 equals 0. That's one way to do it. And this gives you y equals 0. This gives you x equals 1. And now we have to back substitute into this equation. 2x minus y squared equals 0. When y is equal to 0, it gives you 2x minus 0 equals 0. X equals 0. If you plug 1 in here, it gives you 2 times 1 minus y squared equals 0. Y squared equals 2.